zero-shot and few-shot action recognition. Firstly, I'll define the problem. Zero-shot action recognition tries to build models that can classify videos into categories even though it has not encountered that particular category in the training phase. That is, we do not see examples of certain classes during the training time. A few-shot action recognition problem addresses a relaxed condition wherein a handful of samples from seen classes are available. To uniquely identify these unseen classes, we assume side information about them in form of attribute vectors that describe each class. Attribute vectors can either be human annotated or word representations of the class names. Motivation for a zero-shot problem is as follows. The primary motivation is that it is difficult to collect examples from all possible classes, and that several fine-grained classes come up every day depending on the application one is concerned about. And another reason is that humans excel at zero-shot learning. When I describe a new activity to a person, even though he hasn't seen that activity before, he can identify that activity from a video. Our contribution is as follows. By assuming that the video features are Gaussian distributed, we propose a generative approach to zero-shot learning problem. And this, there is nothing sacrosanct about Gaussian distribution, and our model works for other distributions also. We extend the proposed model to the transductive setting. In the transductive setting, we assume that unseen class data is available, but it is not labeled. Our model also naturally extends to few-shot learning, wherein we have few examples. And since our model is generative, we can synthesize novel examples of any unseen class. A brief literature survey would be as follows. There are primarily three kinds of models that address zero-shot learning. Linear models use a linear projection from attribute space to image space. Non-linear models use a non-linear projection in form of neural networks or otherwise. And there are other hybrid methods recently proposed. The architecture of the proposed model is as follows. We divide all the classes into two categories, seen classes and unseen classes. Seen classes are used during training, and the model never sees the unseen classes. We learn a linear projection from the semantic space, which is the attribute space, into the visual feature space, and we also encourage reconstructability of the semantic space features, semantic feature vectors from the visual feature vectors using a reconstructability regularization. The methodology is as follows. We assume, as I mentioned before, we assume that each class comes from a Gaussian distribution, and that the parameters of the Gaussian distribution are estimated from the class embedding vector or the attribute vector using a linear projection. We minimize the following objective function, wherein the projection of the seen class attributes should be close to the seen class image features, which is the first term. Then there is the standard ridge regression regularization, and then there is the reconstructability regularization. In the transductive setting, we use domain adaptation to improve the estimates of our to improve the predicted estimates. To this end, using the unseen data, we follow the expectation maximization algorithm to improve our estimated parameters. Using the unlabeled data, we iteratively improve our estimated mean and sigma. This is similar to the standard EM algorithm used for clustering. And our model also naturally extends to few-shot action recognition, wherein if we are given a few examples of a particular class, we use them to correct the estimated mu and sigma. This follows from the maximum likelihood estimate given the extra data. Coming to experiments, we experiment on the standard UCF101, HMDB51 and Olympic datasets. The details of the datasets can be seen in the slide. In the inductive setting, we achieve state-of-the-art results on all the three datasets. For HMDB, there are no human annotated attributes, and therefore we experiment only with the class embedding vectors obtained using word-to-vec method. In the transductive setting, also our results are state-of-the-art, except on the UCF101 dataset where we are slightly lagging. In the generalized zero-shot setting, we achieve state-of-the-art on all the three datasets using both the attributes as well as the word vectors. On few-shot learning, our results are comparable to supervised learning, even by using as simple as few as just 5 samples. The conclusion is that we have presented a simple probabilistic generative model, and that the proposed model works well on all the data sets across the across the standard settings of the zero shot literature, and the proposed model also generalizes to few shot learning as well as